Related rates questions involving trigonometry. Two sides of a triangle have lengths 15 meters and 20 meters. The angle between them is increasing at pi over 90 radians per second. How fast is the length of the third side changing when the angle between the sides is pi over 3? Let's draw a diagram. The two sides of the triangle, 15 and 20, angle between them increasing. How fast is the length of the third side changing? Now go way back in your memory banks. Two sides, angle between them, finding the third side. If you remember the law of cosines, that allowed you to find the third side when you knew two sides and the angle between them. It looks a lot like Pythagoras, but with this extra term. Now, if you're looking at this and saying, how on earth am I supposed to be comfortable with all these equations that you're throwing at me? The more questions you do, the more familiar these equations will become. So keep doing all the questions. Now, there's a lot going on, so let's put in any information we can. The 15 meters of the triangle can go in because it is not changing. So let's put the 15 in for A and the 20 in for B. 15, 20, there's another A, that's 15, and another B, that's 20. If you are tempted to put in the pi over 3, let's talk about why you cannot. The angle between them is increasing. So anything that changes must remain a variable until you have taken the derivative. So we put in 15 and 20 because they were constant, not changing. We leave the angle as a variable because it is changing. Let's clean this up. 15 squared, 225. 20 squared, 400. 2 times 15 times 20, 600. 225 plus 400 is 625. And we'll stop there. If you were tempted to subtract 600 from 625, you'll realize that because there's a cosine C attached to the 600, that we cannot do that. So this is as simple as this equation is going to get. Now it's time for the derivative. Let's look at that rate. It's seconds in the denominator, so we want to take the derivative with respect to time. Derivative of c squared with respect to c multiplied by the derivative of c with respect to t. Derivative of c squared is 2c multiplied by derivative of dc dt. Derivative of 625 is 0. There's no variable. Derivative of negative 600 cos angle. Derivative of cosine is negative, so we'll get negative negative or positive 600. Derivative of cosine. Derivative of angle. Derivative of c with respect to t. I'll do that again. Derivative of c squared. Derivative 2c times dc dt. Derivative of 625 is 0 as there's no variable. Derivative of negative 600 cos, negative 600, sine, angle, derivative of angle. What are we looking for in the question? How fast? That means d's are involved because that represents a change. The length of the third side, that's c, so it means we're looking for dc dt. Change in side length over change in time. Let's get dc dt by itself by dividing both sides of the equation by 2c. Now plug in anything you know. dc dt, that is change in angle over time, that'll be pi over 90. Angle c is the pi over 3, which we're allowed to plug in now because we have taken a derivative. Unfortunately, we don't know what c is. This is quite common in questions that you'll reach this point, you'll plug in all kinds of information, and there is still something missing. In these situations, go to the equation just before you took the derivative. When we do that, we can usually find the information we need. Angle C is pi over 3. The cosine of pi over 3 we know. 60 cosine 60 is a half. A half of 600 is 300. Take that from 625, you'll get 325, and now we'll take the square root. When you take the square root, there'll be a 13 times 25 under the square root. 325 is 13 25s. And you know the square root of 25 is 5. So that's where this came from. I'll try that again. The square root of 325 will be the square root of 13 times 25. But the square root of 25 is 5, so we'll pull that out and put it out front. You'll notice we didn't bother with a plus or minus, and that's because we know C as a length has to be positive. All right, I'm going to start the next slide with this, and we'll keep going. What can we do now? 5 root 13 can go in for C. The sine of pi over 3 we also know. So the sine of 60 is root 3 over 2, and C was 5 root 13. Time to clean this up. Fractions as part of fractions. We've never liked that. We have a 2 and a 90 in the denominator, which is 180. So let's multiply top and bottom by 180 to get rid of the 2 and the 90. When we do that, the 2 and the 90 in the denominator get eliminated by the 180, and the 180 in this part of the fraction gets multiplied by 2. If you would like to do this without using a calculator, 600 and 360 have a common factor of 120. And when we divide by 120, we'll end up with 5 and 3. And then those 5s can also get eliminated. Clean that up, and we have root 3 pi over 3 root 13. Now, for those who are saying, I just use my calculator and I have no idea if I'm right, continue to use your calculator and get a decimal answer. Check the answer, make it a decimal, and if your 2 decimals match, then you know you're fine. No need to worry about what I'm doing. We always answer in words. Change in the side length. I believe the side length was measured in meters. Time was measured in seconds. So the third side is increasing at root 3 pi over 3 root 13 meters per second. Increasing because it's positive. And that should make sense. If you were looking at the triangle and the angle was getting bigger, then the side between them will also be getting bigger. Let's try another one. A revolving beacon is situated 925 meters from a straight shore. It turns at 2 revolutions per minute. How fast does the beam sweep along the shore at its nearest point? How fast does it sweep along the shore at a point 1275 from the nearest point? So we're really doing part A and part B of this question. A revolving beacon, imagine a lighthouse, situated 925 from a straight shore, such as a beach. And this would be the light that would sweep along the shore as the lighthouse, as the light turns around. All right, the angle between the beam and the line that you're imagining connecting the lighthouse to the shore, the distance along the shore. So we're putting in variables for things that are changing and things that we care about. Never really talked about that distance at all, so there's no point in putting a variable in. Theta is the angle between, that's how fast it's turning, so we care about that angle. X is the distance along the shore. 925 is the distance the lighthouse is from the shore. It doesn't change, so we put it in the picture. Now, what can we do here? We could probably use trigonometry. I have an angle, I have an opposite side and an adjacent side. So that looks like tangent. Tangent, opposite over adjacent. If we multiply both sides by 925, we can get rid of the fraction. We'll take a derivative. Derivative of tangent is secant squared. We'll get to that in a minute. We're going to take the derivative first with respect to theta, then chain it with d theta dt. Derivative of x we'll take with respect to x, and then chain it with dx dt. Derivative of tangent, secant squared. And now, what do we know? At the nearest point. If we were at the nearest point, this line would not be 1275 away at all. It would actually be here. That would be the nearest point. And the angle between this line and this line, if we move this over, would actually be 0. So again, what just happened? At the nearest point, the beam wouldn't be over here at 1275 because that's not at the nearest point. The nearest point would be right here, which means the angle is 0. All right, secant squared 0. Secant squared 1 over cosine. Cosine is 1. So secant is 1, and secant squared is 1. What are we looking for? How fast does the beam sweep along the shore? Fast means involving d. Beam along the shore was x, so that's dx dt. No need to solve for anything. We just plug in what we know. Now, d theta dt. It's changing at 2 revolutions per minute. So it goes around once and twice every minute. So how big an angle does that cover? Once around is pi. Twice around is 2 pi. So it covers, let me try that again. Once around is 2 pi. Twice around is 4 pi. So it covers 4 pi degrees, or radians, which is what theta represents, the angle, every minute. So that's how d theta dt became 4 pi. Multiply that out, we get a beautiful answer of 3,700 pi. Feel free to leave your answer that way. Or for those who are liking decimals, 11623.883. So the answer to our question in words, the beam sweeps along the shore at 11624. X is distance, it's measured in meters. Time, minutes. So 11624 meters per minute. Let's do a little review of that. Beacon, 925. Beam sweeps along shore. That's a distance that's changing. Angle is changing. We looked at the picture and thought we could probably use trig. Didn't know anything about that side, so we can't use sine or cos, but we can certainly use tangent. Got rid of the 925 to avoid a fraction. Took a derivative with respect to theta first, then d theta dt, x first, then dx dt. We figured out that at the nearest point, if that beam was over here, the nearest point would give us an angle of 0. Calculated the secant of 0 at 1, squared it, still 1. Change in the angle, 2 revolutions a minute. Once around is 2 pi. Around again is another 2 pi. So it's changing 4 pi. Multiplied it out, got a decimal if you want. What if we do the question, how fast does it sweep along the shore at a point 1275 from the nearest point? We still start the question the same way. So we can pick up from this point. 925 secant squared, and where's this 54 degrees coming from? We have 1275 now in this question. If you put 1275 in over 925 and do inverse tan, the calculator will give you an angle of 54 degrees. You can then calculate the secant of 54. Secant of 54, 1 over cosine 54. And if secant was squared, so is cosine. And then you can work that out on your calculator. So we calculate the cosine of 54, square it, divide 925 by that, and that gives us 2677.345. d theta dt. How fast is that beam moving? 2 pi and 2 pi again, because it's still 2 revolutions per minute. That gets multiplied by 4 pi. And there's our answer. So the beam sweeps along the shore at 33644 meters per minute when you're at this point. Faster than when you're at that point. Your job. We're going to continue on with related rates 2 and finish it. And we're going to start related rates review number 1, 1 to 5. If you have any questions, just let me know.